So what I want to do is to prove this kind of inequality so the homomorphism density of a 6 cycle or any even cycle is at least the density of K2 in G raised to the 6th power, or the appropriate power if it's a longer even cycle. I want to prove this, but I don't want to do it in this way because I'm not going to be able to do it yet. So I want to kind of give you another method for proving these kinds of statements. So we're going to be using linear algebra. Okay, so probably this is a definition people have seen before. So the adjacency matrix of a graph. So in general, right, the adjacency matrix has a row for every vertex and a column for every vertex. And if you look at the row corresponding to vertex u and the column corresponding to v, if you look at that entry, it's 1 if and only if u is adjacent to v. Just to make the rows and columns kind of, so I can talk about the first row, second row, it just makes my life a little easier. I'm going to think of the graph as the vertex set as being the numbers 1 up to n. So the adjacency matrix of G is the n by n matrix, where the ij entry is 1 if ij is an edge and 0 otherwise, right? So I don't know, if I have a triangle 1, 2, 3, let's say, or maybe there's a better example on the next slide. I can't remember, but I think if you have a triangle, everything's adjacent. Oop, why did I write it 2? 1, 1, 1. I've got 1s everywhere except the diagonal, which is 0. So if G is that, then that's my adjacency matrix. Probably, maybe not everyone's familiar with this. I'm not sure. If you've taken graph theory, you're probably familiar with this. But basically, this gives you a way of representing a graph as a matrix. Okay, so if I've got this graph, okay, can anyone help me fill out the first line of this? So 1 is not adjacent to 1. I mean, generally, we're going to have zeros on the diagonal. But yeah, what do we got here? Right, 1, 1, 0. The 0 here just is because 1's not adjacent to 4. Right, and so on and so forth. I mean, basically, this is the same kind of 3 is adjacent to everybody, and 4 is only adjacent to 3. Okay. Well, here's the thing about the adjacency matrix, right? It's always symmetric, in the sense that, you know, the ij entry is always equal to the ji entry, because if I is adjacent to j, then j is adjacent to I, right? We're not dealing with directed graphs here. Everything, if the adjacency relation is symmetric. So the matrix is symmetric. Is there a 3? Oh dear. Probably because I was tired when writing these slides up. But yeah, there should not be a 3 here. I wish I could say that I planted that to see if anyone was paying attention, but I didn't. Thanks. There shouldn't be a 3. Now here's just a small thing, but I mean, it's wrong to say that the adjacency matrix of a graph is unique in some sense, because the adjacency matrix depends on how you label the vertices in some sense. Okay, here I'm dealing with graphs with vertex set 1 up to n, and then it's pretty clear how I should organize the vertices. But for a general graph, I mean, the matrix depends on how I choose to organize the vertices, if that makes sense, or order the vertices. Okay. Remember this whole matrix multiplication thing? It does depend only up to row and column swaps, but there's a sneaky thing that you have to, when you swap the rows and columns, if you swap the 3rd row in the 10th column, you have to swap the 3rd row in the 10th row, then you have to simultaneously swap the 3rd column in the 10th column at the same time. So, because that's going to keep the symmetry and stuff. So it is up to those kind of swaps. Okay, so remember this whole matrix multiplication thing. So how do I get matrices A and B? How do I get A times B? So if I look at the ij entry of AB, A times B, it's the dot product of the ith row of A and the jth row of B. I'm just going to deal with n by n matrices, but obviously matrix multiplication is more general. You can deal with non-square matrices. But yeah, so dot product, right? You just take this one multiplied by the first one here, multiplied by the first one, second multiplied by second, and you add those things up, and then you just write that in this entry. Okay, I do need all this linear algebra stuff, so this is just kind of review. Okay, in other words, the ij entry is the sum. So if a is equal to, aij overall ij from 1 to n, and b is the b is equal to bij, right, overall I and j, then the ij entry of a times b is this sum. Okay, so now let's connect this to graph theory. Okay, so here's my question. What is the ij entry of AG, the adjacency matrix of G squared, in terms of graph theory? Yeah, so there's an answer in the chat which says walks. And yeah, so that it's the number of walks of length 2 from vertex I to vertex J. And I think the best way of thinking of it is in terms of this sum, maybe, right? If I look at, so here, okay, if I'm dealing with just the square of the same matrix, I've got AI k, ak j, and we're summing over all k from 1 to n, right? This thing is going to be 1 if, so in an adjacency matrix, the I, say 2 thing is 1, like if k is equal to 2, I2 is 1 if and only if that edge is there. And then from 2 to j is going to be 1 if and only if the edge is there. And so every term here where I get a 1 corresponds to a vertex which is like between I and j on a walk of length 2. Yep, that'll also work. So number of walks of length 2 from I to j, or also it also is going to be equal to this. Yeah, I guess that in this case I'm kind of preferring the walk terminology because it's going to generalize nicely. But yeah, in this case it is also equal to this. So is it clear why this thing, the square of the matrix, counts walks of length 2? Because basically it looks for the middle vertex and it counts all possible middle vertices, and it's going to count each of them exactly once. Okay, so let's give a kind of formal proof of the following lemma, that the ij entry in the kth power of the adjacency matrix is equal to the number of walks of length k from vertex I to vertex j. And this is fairly, the way we're going to do this is just by induction. So in the base case, k is 1, right? So then we're just dealing with the first power of the adjacency matrix. Now, obviously, if I have 2 vertices, there's a walk of length 1 from I to j, if and only if I and j are adjacent, right? And you can't have more than one walk of length 1 between them because there's no multiple edges. So the case k equals 1 is okay, because a walk of length 1, well, let me just say, maybe I'll just write this, that the number of walks of length 1 from I to j is equal to, so I to j is 1 if they're an edge, if they make an edge, and 0 otherwise. But that's equal to the ij entry of A. So this is a bit messy, but okay. So now let's look at the general case. And the general case is not too bad, right? Because basically the idea is, if I want to get a walk of length k from vertex I to vertex j, that's the same thing as picking an intermediate vertex, let's say, well, I don't know, I'd probably give it a name, L, and counting ways to go from I to L in k minus 1 steps, times the number of ways to go from L to j in 1 step, which is actually just 1 if and only if there's an edge. So the ij entry so in the general case, so this is just by definition of matrix multiplication, that the ij entry of the kth power is, so you sum over all L, you take the IL entry of the k minus 1 power times the LJ entry of the adjacency matrix, so just the first power. So this is just by, matrix multiplication, which is just by induction the number of walks of length k minus 1 from I to L. So L is the thing we're summing over, times, number of walks of length 1 from L to J. Then you just have the observation that a walk of length k from I to j is the same thing as walking k minus 1 steps to some vertex L and then walking 1 step to j. So that is equal to the number of walks of length k from I to j. Is that clear? So it's just summing over all of the possible choices for the penultimate vertex of the path. Okay, this stuff all sounds almost kind of boring, but it's going to be kind of powerful. So here's what I want to think about now. What if I just look at the I entry of the kth power of the adjacency matrix? And okay, by what we've said, this counts walks of length k. Oh, sorry. This should just be the word walks of length k that start and end at vertex I. But what is if you think about what is a walk of length k that starts and it ends at vertex I? Well, yeah, it's basically a cycle, but it might not be a cycle because it might reuse some vertices. But actually, it's kind of a homomorphism of a cycle into the graph, which is kind of rooted at vertex I. So suppose I let the cycle, so I'm going to denote the vertices of the cycle for whatever reason as u1, u2 up to uk. So the number of walks of length k that start and end at vertex I is going to be equal to the number of homomorphisms from ck, cycle of length k, into g, such that the first vertex of the cycle is vertex I. Okay. So closed walks that start and end at vertex I are the same thing as homomorphisms from a cycle where the first vertex is I. So actually, this adjacency matrix gives us a way to count homomorphisms of cycles. So I mentioned this definition before, but the trace of a matrix. So the trace of an n by n matrix is the sum of the diagonal entries. And so let's talk about the trace. So I'll make a poll. So right. So what is the trace of the kth power of the adjacency matrix of G? So building up all the stuff we've done so far. So it's probably something with cycles, I guess. But yeah, so what we showed before is that the I entry of this thing is the number of homomorphisms from ck into G, such that the first vertex, let's say, so for whatever reason, again, I'm defining my cycle, the vertices to be u1, u2 up to uk, right? So if I add that up over all values of I, then if I add that up over all possible values of I, that's going to count every homomorphism exactly once, because, the II entry counts the ones which happen to map the first vertex to I, and the first vertex can only map one place, right? So this is going to exactly count all of them exactly once. Okay, so all of these answers look sort of right in the poll, but only one of them actually is. So it is equal to the number of homomorphisms of ck into G. So it's not k times that, because it's kind of k times the number of, it's still not quite right, but I was going to say it's kind of like k times the number of cycles, but it's still not quite right because you can use the same vertex more than once in a homomorphism. So it is the number of homomorphisms. Any questions about that? Yeah, exactly. It's just another way of writing the same thing. Okay. So as a corollary, if I take the trace of the kth power and I divide it by n to the k, that gives me my homomorphism density. Remember, homomorphism density is just the number of homomorphisms divided by number of vertices of G over to the power of number of vertices of H, where H is ck. So you just use this equality and then divide by n to the k, and just by definition at this point, by definition of THG, we're done. Okay, so this whole thing about, remember, I want to try to bound this thing from below. Now everything kind of becomes, trying to bound some function. So, this sort of function of the adjacency matrix below by, so I want to prove that this is at least, 2k here. So everywhere here I'm dealing with cycles of length k. So everything I've done so far, the cycles could be odd or even. But in the theorem that I want to prove, we're dealing with even cycles, right? But basically, yeah, so this boils everything down to a problem involving the adjacency matrix. What I want to do now is take this problem involving the adjacency matrix and turn it into, well, and kind of try to understand this in terms of the eigenvalues of the matrix. At least I think that's what we're going to do now. Yes, okay. I don't have a good answer for that. Yeah, I mean, actually, I don't think, so here's a silly thing, but, and this may not be quite necessary for this, but I think kind of computing matrix multiplication, I don't think people know how fast you can do that. Just saying, can I compute the product of two matrices? Okay, but here we're only asking for the trace in your question, and we're only dealing with adjacency matrices, which changes things. But yeah, so I don't have a good answer to that. Okay, yeah. I guess equally as fast as you can count paths of length k, or closed walks of length k, but yeah. Okay, so remember what eigenvalues are. So eigenvalue for a matrix, so lambda is an eigenvalue for A if there exists a non-zero vector such that A times that vector is lambda times that vector. In other words, basically applying A to the vector V, all it does is stretches or compresses the vector V by a factor of lambda. That's what eigenvalues are, right? It's what eigenvectors are as well. So V would be an eigenvector. So V, an eigenvector corresponding to lambda. Okay, so this is again from linear algebra. Yeah, okay, so every n by n, I want to kind of remind you that every n by n matrix, it does have n eigenvalues, okay? They might not be different, so you can have the same eigenvalue appearing multiple times, but they do have n eigenvalues, always, okay? There is a slight catch that those eigenvalues might not be real, okay? They might be complex numbers, but you always have n real eigenvalues. So why? This is again some more reminders from linear algebra. I'm sorry if this is extremely boring, but we kind of need all of these things. Okay, I don't really need the proof of this, but I'm just saying it anyway. Remember the characteristic polynomial? So for a matrix A, you get a polynomial in lambda by you take A minus lambda I, where I is the identity matrix, the n by n identity matrix, and you take the determinant kind of as a function of lambda, right? And then you think about this thing that the determinant is 0 if and only if there's something in the null space, if and only if there's or something non-zero in the null space, if and only if there's a non-zero vector such that this holds, which is the same as lambda v. Okay, anyway, the point is that the determinant is a polynomial of degree n, and the roots of this polynomial are exactly the eigenvalues of A. And if you have a polynomial with degree n, where the term corresponding to lambda to the n has a non-zero coefficient, it always has n distinct eigenvalues, right? Does anyone know this thing, fundamental theorem of algebra? Like if you have a polynomial of degree n, it's got n roots, always. They might be complex, right? They might not be real, but there's n of them, is the message. Okay. Now here's a cool thing about adjacency matrices. So I don't like dealing with complex numbers. Probably you don't like dealing with complex numbers. I mean, to be honest, we're all in a combinatorics course, which probably tells me we all prefer dealing with integers. But anyway, so complex numbers are kind of a pain, but we don't have to really deal with them here because if you have a symmetric matrix, so this is a fact from linear algebra that I won't prove here, but all of the eigenvalues are automatically real. And adjacency matrices are symmetric, so therefore, if you have an adjacency matrix of a graph, then you can assume immediately that you have n real eigenvalues. Okay, they might not be distinct, they might be positive or negative or whatever, but you have n of them. Okay. Oh, here's a question to kind of test just a bit of linear algebra knowledge, I guess. Okay. Okay, so like I said, we've got n different eigenvalues of an n by a matrix. Suppose I know the eigenvalues of A. what can I say about the eigenvalues of a squared? So yeah, on the slide I've got them written as lambda. In the poll I've got them written as L. But so if you have forgotten this, which I mean, I'm not sure if this is ever something you would have memorized in the first place, but like you can actually work this out by thinking about the definition of eigenvalues, right? So you don't actually need to have like remembered this from, yeah, maybe you can. You don't have to like somehow have remembered this fact from linear algebra or something. This is something you can just work out from the base principle. Because like, let's just take vi, an eigenvector. So take for lambda I. What happens if I take a squared times vi? Well, okay, there's a subtle thing here that this matrix multiplication is associative. I can apply the multiplication in any order I want. So I can say, okay, this is the same as a times vi, which is the same as a times lambda vi, or lambda I vi, because it's an eigenvector, right? So this is because a vi is lambda I vi. That's all I'm using there. And then I just kind of do it again, and this scalar just kind of sits there, right? And it gets squared. So this is just lambda I squared vi, which tells me that if lambda I is an eigenvalue for a, then lambda I squared is an eigenvalue for a squared. I'm not sure if it completely gives you the association between them, but the fact that, again, this fact that like a real or a matrix has n distinct eigenvalues, I think that gives it to you that literally the eigenvalues for a squared must be lambda 1 squared, lambda 2 squared, lambda 3 squared, up to lambda n squared. I think you can put the pieces together to get that proof. But yeah, so the answer is like lambda 1 squared, etc., up to lambda n squared. So there's one more thing. Okay, this is what I just said. So maybe I'll start trying to prove this theorem about cycles of length 2k, and we'll kind of do some linear algebra as we go. I've only got like 4 minutes, so I'll probably just start this and then go back to the start and start it again next time. But okay, so what do we want to prove? We want to prove that for every k at least 2, every graph G satisfies the density of cycles of length 2k in G is at least the homomorphism density of k2 raised to the power 2k. So this is our goal. So we already came up with an expression for this homomorphism density. So T, like homomorphism density of a cycle of length 2k is equal to the trace of the 2k power of the adjacency matrix over n to the 2k. Now, I want to link this to eigenvalues. Does anyone remember anything about eigenvalues and traces? Maybe not. Yeah, it's extremely vague. My bad. Yeah, it is the sum of the eigenvalues. Yeah. And the reason for it is given in the chat, that if I change the basis of say I take a matrix and I change to some other orthonormal basis or something, then that preserves the trace. And that's the key thing. And if you have n eigenvalues, I can change to a basis where the matrix becomes a diagonal matrix with those eigenvalues on the diagonal, and that change preserves the trace. So, right. So for any n by n matrix, the trace of m is equal to the sum of the eigenvalues. But that's great that I also got a reason for it as well. Okay. Right. So I can rewrite this thing. So, and also I know that like if I look at the eigenvalues of the 2k power of the adjacency matrix of G, that's just the 2k powers of the eigenvalues of the adjacency matrix of G. So it's just like, so I've got this thing, I've now got my homomorphism density written as a function of the eigenvalues of the original matrix, the adjacency matrix of G. Okay. This is kind of where the evenness of the cycle comes in, because we're going to use that, at some point we're going to use here that, like if I take a real number, so remember these eigenvalues are real because this is symmetric. So these are all real numbers. If I take an even power of a real number, it's non-negative. So that's kind of giving me, yeah, that means that I can kind of that helps me to analyze this numerator here. For example, what I could say is that if I just look at the first term, like the term with lambda 1, I can say that it gives me a lower bound for the whole thing. So so lambda 1 is the largest eigenvalue, let's say. So all the other terms, the lambda 2, lambda 3, etc. terms, because they're raised to an even power, those are all non-negative. So I can say that this is at least lambda 1 to the 2k over n, or over n to the 2k, and then I just put them all under the power, which looks super, super wasteful and like a completely crappy bound. But this is actually going to give the result at the end. So we're trying to lower bound this thing. The homomorphism density of a cycle of length 2k into g. That's where we were at. And what did we prove so far? So we kind of had already proved two things, right? We proved that so this was like the first thing we did. We showed that the homomorphism density of a 2k cycle into G is just the trace of the 2kth power of the adjacency matrix over n to the 2k. So that's, I mean, the denominator is just what you get by dividing stuff. Like the numerator is the important part. Like, so the numerator is the number of homomorphisms of C2k into G, and we just divide by the appropriate thing, right? And the reason for that was that the II entry of this adjacency matrix to the 2k power, what it counted was closed walks of length 2k that start and end at vertex I. And if you count up all the closed walks of length 2k that start and end anywhere, that's going to, if you add all of those up, that's going to give you the number of homomorphisms of a 2k cycle into G, because a 2k cycle homomorphism is just a closed walk. It's really the same thing. And then we said the second thing, and this was all facts about linear algebra. So the trace of this 2k power, which is this numerator that we're interested in here, is just the sum of the 2kth power of the eigenvalues, where the lambda 1 up to lambda n are the eigenvalues of the adjacency matrix. Okay, and that's because, so to do this, we had to also say that if these are the eigenvalues of the adjacency matrix of G, then the 2kth powers of these are the eigenvalues of the 2kth power of the adjacency matrix. And that was an easy thing, just using the definition of eigenvalue. So this is kind of just recap. And the reason for this, because the trace is the sum of the eigenvalues, and the eigenvalues of this thing are those, the powers of the eigenvalues of the original adjacency matrix. So this is where we were at. We had this equality, and this is not an inequality. This is just equals. So this stuff, these things are equal. Here's a very basic fact that I guess everyone is hopefully aware of. If I take a real number, well, imagine you take a real number and you square it. That's non-negative, which, I mean, I remember being surprised about that in elementary school, right? When you take a negative 1 and you square it, it's positive. I mean, but anyway, so if you take a real number to an even power, it's always non-negative. So that allows us to get a lower bound on this expression. Oh, because, so one thing we also mentioned last time is that the eigenvalues, and this is important, so the eigenvalues of a G are real. And this is because the adjacency matrix is symmetric. Okay, so if you had any matrix there, which is not symmetric, it might have complex eigenvalues. And if it had complex eigenvalues, we couldn't use this fact, because if I take the square of a complex number, it can be negative, which is annoying. But are you all with me now still? Okay. So what I can do here is I can lower bound this expression by just taking the biggest eigenvalue. So let's say I let lambda 1 be the largest eigenvalue. I can say that this whole sum on the top is at least lambda 1 to the 2k, and then I've got the same denominator. I see what you mean. Yeah, right. If I was trying to multiply this by n or something, it'd be the other way around. Yeah. So to get this inequality, what I used is just that that lambda I is non-negative for I from, let's say, 2 up to n. Okay, so I just threw, it looks like I threw away a lot, right? I threw away every term of the sum except for the first term, which looks a bit crazy. Okay. So what I want to do is show that lambda 1 is big. Okay. If I can show that lambda 1 is big, then that gives me a good lower bound. The bigger I can show that lambda 1 is, the better lower bound I get on this thing. I'm not even sure what principal eigenvalue means. It probably means that sounds like it really means something, but I guess it's equal to the spectral radius or something, if you like that terminology. But anyway, the thing is, all the eigenvalues are real, so it's fairly easy to say what's the biggest one. If they were complex, then it'd be confusing because there's no biggest complex number because they're all scattered around 2 dimensions. But yeah, so it's just literally the biggest one. Maybe it's called the principal one. Probably it's called the principal one. Okay, so this is where we've gotten so far. So if we can prove this inequality, that lambda 1 is at least the K2 density of G times n, then so what that'll give us, if we kind of plug it in here, is that this would be at least the K2 density to the 2K power, which is what we set out to prove. And later we'll talk about why this is actually tight. So in some sense, it feels like we're throwing away a lot, but actually we prove a tight inequality at the end. Okay, so our whole life's goal at this point boils down to proving that this biggest eigenvalue is at least this. Okay, maybe it's dramatic to say it's our whole life's goal, but for the time being. Okay, so now a bit more linear algebra comes back. So this is another statement that I'm not going to prove. I mean, I considered proving it, but yeah, it requires too much linear algebra. Thinking about these, change of basis, and I mean, it really can be proved by just thinking about change of basis and stuff like that. But anyway, let's not think like diagonalization basically is what I'm talking about, but let's not think about that. But here's a fact from linear algebra. If A is a symmetric matrix and lambda 1 is the largest eigenvalue of A, then there's actually a nice way to kind of describe it. So the largest eigenvalue is equal to the maximum overall non-zero vectors. So V is you have to take non-zero vectors, otherwise you'll be dividing by 0 here. You'll have all kinds of problems. So take a non-zero vector and look at A times V dot product. So these square brackets or these pointy brackets are just the dot product. I could have written it like this. I don't know what people prefer. Maybe they prefer that. But yeah, so lambda 1 is equal to this. So if we just take this fact as being true, if I want to lower bound lambda 1, I want to show it's greater than or equal to something. It's not so hard to, there's a natural thing to try, which is to pick a vector v where like this ratio is large. The ratio doesn't, the fact that it's dividing by v times v doesn't really matter, or v dot v doesn't really matter here, because you can just think about unit vectors and everything's the same. But anyway, I want to take a vector where basically this is large. Is that clear? And then I'll have a lower bound on lambda 1. So here's the vector I'm going to take. It's not a very inventive one, but I'm just going to take the all ones vector. So let's think about what happens. So V is the all ones vector. It should be a column vector, so I can apply this multiplication. So what do we get? Yeah. So what is that in terms of the graph? I guess I'm asking. So I think you're both kind of saying the answer at the same time. So yeah, the first row or the first thing here is going to be the degree of the first vertex. So I guess I'm dealing with vertex set, let's say 1 up to n is the vertex set of G. And yeah, this will just be the degree in G of the vertex 1 and then 2, etc. Because it's just the sum of the first row, which is just the degree. And now if I dot product that with V, which is the all ones vector, I get the sum of the degrees, which is by handshaking 2 times the number of edges. So plugging that in, you get that, that is a nice equivalence. it's very dependent on the vector v that I chose here. But yeah, it ends up just being the number of edges. So 2 times the number of edges. So the numerator here in this thing is 2 times the number of edges. If I do v dot v, where v is the all ones vector, it's an all ones vector of length n. So you just get n. And now if you think about that, that is literally just equal to this. Because remember, tk2g is 2 times the number of edges over the number of vertices squared. And this is like the same thing, except that there's no squared here. So it's this thing times n. So, okay, so we're happy. We can just plug it in. Homomorphism density of a 2k cycle is at least, so it's equal to these two things at the top, which is at least, if you just take the first eigenvalue, which is then at least this because of that fact about, because when we took that all ones vector, that's where we get this. And then this is just equal to that. No, that's fine. Okay, any questions about that? Yeah, it feels super wasteful, right? Because we've thrown away, we had n eigenvalues that we could have used. We threw away n minus one of them, and we just kept the biggest one. But actually, there's a lot of reasons why that was actually a natural thing to do. I'm not sure if I'll be able to express that well, but I can try. First of all, okay, how wasteful was it? So to kind of tell you why it's not very wasteful, we can give an example which is almost tight. I mean, it's asymptotically tight as n goes to infinity. Right. Maybe I didn't put an example here. Well, let's talk about an example. So the example here is the same as the example for C4s, which was a random graph. So let's say that G has n vertices. If I take ij, it's an edge of G with probability P, and all of these things are independent. So yeah, one edge being there doesn't influence the other. It's just flip a coin for every edge. So my expected value of tk2g, well, tk2g, we know that that's just twice the number of edges over n squared. And basically by linearity of expectation, I can take the expectation inside, and then we just are asking how many edges do we expect, which is going to be p times n choose 2, because every edge, by linearity of expectation again, every edge is there with probability p. If you add up some kind of indicator variables or whatever, anyway, it's going to be p times n choose 2. So we have 2 times p times n choose 2 over n squared, which is roughly p, right? So that's our edge density, and then the expected value of the C2k density. So this one maybe I'll be a little bit quicker and a little bit less precise in how I kind of view this, but if n is very large, imagine I map 2k vertices into G, where the number of vertices in G is really, really large. It's like taking all the people in the world and picking 20 of them with replacement. Like I pick somebody, I then am allowed to pick them again or somebody else. You're never going to pick the same person twice because there's way too many people. Like the probability of doing that's non-zero, but it's basically zero. So basically if n is very large, then all of the maps here are injective, meaning, if n is large, then practically every map from a set of size 2k to a set of size n is injective. And now if I look at an injective map, let's say k is 3, for example, the probability of, if I pick, suppose I pick, where the vertices 1 up to 6 go in G, the probability that this is a homomorphism is the probability that all of these 6 edges are there, which has probability p times p times p because of independence. So this is going to be roughly p to the 6, or sorry, p to the 2k in general. So this is again to say that as n goes to infinity, if you take a random graph, the homomorphism density of a 2k cycle will tend towards p to the 2k, whereas the edge density will tend towards p as n goes to infinity, which I know people maybe don't love, but that shows that it's basically tight, at least in an asymptotic sense. Which, yeah, anyway. Yeah, if you think about it though, another way to say that, so if I have so we proved this inequality, right? Like one way to kind of understand when an inequality is tight is to kind of go backwards through the proof, right? If you go backwards through the proof step by step, you can say, okay, this inequality is tight if and only if all of the inequalities in the proof are tight. So in particular, like if you have a graph G where this inequality is close to tight, then basically what has to happen is that the first eigenvalue of that graph has to be pretty much equal to the K2 homomorphism density of K2 times n. Because if it was significantly bigger, we would have a better lower bound. So if it's tight, then basically lambda 1 is equal to this. And all of your other eigenvalues are small, meaning that they're kind of negligible compared to lambda 1. Is that kind of clear? Oh, that's actually a good question. So no. Oh yeah. So when I say that's a good question. So I'm thinking of these things as being positive because when we're dealing with cycles that are even, we're looking at their 2kth power, which is positive. But these things aren't positive. So when I say small, I mean they have small absolute value. So they're close to 0. But that's yeah, that makes, and they could even be 0. But by the way, you know that some of them have to be negative because remember this thing from this Peterson graph example. So if I take the trace of the adjacency matrix, it's 0 because the diagonal is 0. And the trace is equal to the sum of the eigenvalues. So if this one's positive, then you actually know for sure that some of these things are negative because they have to cancel out to be 0. Just a kind of comment. But basically, yeah, the way it'll work in a tight example is that you've got this one big eigenvalue, which is roughly equal to this. And then all of the other ones are small and most of them are negative and they kind of maybe, well, am I right to say most of them are negative? I'm not sure. But basically they need to cancel out this big one. Okay, so what this actually says, weirdly enough, in like a kind of roundabout way, is that if you take a random graph, it's going to have this property. Like, because a random graph is roughly tight for the inequality. So that implies that a random graph must have the first eigenvalue being roughly equal to this and all the other ones being small. Because if it wasn't, then it couldn't be close to tight for the example. So in a weird kind of roundabout way, we've proven that a random graph has this kind of a spectrum in the adjacency matrix has this kind of spectrum, has one big eigenvalue and lots of small ones. I'm not sure if that was clear or not. So we might end up ending early today. So if you do have questions about stuff like exams and stuff, then I might be able to answer them in a few minutes. I'll just mention again, so back when we were talking about force cycles and the homomorphism density of those things, we were talking about Sidorenko's conjecture. I mentioned that like right at the end. So I'll just mention that again. So if H is a bipartite graph and G is any graph, what Sidorenko's conjecture says is in my opinion, this is a really, really beautiful conjecture. Some people are starting to think it's probably false, but I'm not sure whether I hope it's true or false, but actually I guess I hope it's true. The homomorphism density of any bipartite graph H in any graph G is at least the K2 density raised to the power of the number of edges of H, which is exactly what we've been proving for even cycles, right? What we've proven is that, right, that this is at least this, which is, the number of edges in a 2K cycle is 2K. So, okay. And Sidorenko's conjecture, by the way, would be tight if you take a random graph. So for every bipartite graph H, if this thing is true, it's tight because you can take a random graph. So we've just proven this for cycles. And later, but much later in the course, basically at the end, we're going to prove that this conjecture also holds when H is a tree. That is, if we get there. It's the last thing I have planned for the whole course, so we might not get there. We'll see. So this is somewhat the tip of the iceberg in terms of what's known. So there's lots of different results on this conjecture, but still the conjecture is not proved. If you're interested, the smallest case that people don't know the answer to, they don't know if it satisfies the conjecture, is this funny graph here that they call the Mobius ladder. So it's the same thing as taking a K5 and deleting the edges of a 10 cycle. it's called a Mobius ladder because you can think of it as like, so you can also draw this as, kind of, if you imagine rungs of a ladder, and then you have, well, at the last step, kind of, you have these things which kind of cross. Okay, I haven't drawn this very well, but it's kind of like a ladder that goes around back onto itself. Yeah, it's like a ladder that goes around back onto itself, but with one twist. It's like this graph, like a pentagonal prism, if that makes sense, like this kind of prism, except that it's not a prism. It has one twist, but like imagine I just cut this and switch the edges. Okay, and that makes it bipartite. And nobody knows if this conjecture is true for this graph. Actually, oh yeah, so on assignment 4, there's one question about KST, complete bipartite graphs. So you're going to be asked on the assignment, well, you are being asked on assignment 4 to prove this conjecture for KST. I made an announcement about that earlier today, so that's, I would suggest trying to adapt proof that we did for C4, and use the fact, think about C4 as being K22, because C4 is K22. Another interesting example, so it's known for graphs where you have a bipartite graph where there's one vertex on one side adjacent to the other side, adjacent to everything on the other side. So that's a result of Conlon, Fox, and Sudakov. So that actually covers like pretty much a lot of bipartite graphs, right? Take any bipartite graph you want and then add a vertex that's completely joined to the other side, and that satisfies the conjecture, and also hypercubes.